Okay, so this is problem number 3. Forces are applied at points A, B, and C of the bar shown. It is now origin. Okay, so this is now your A. This is your point B. And we now have your point C. Replace this system of forces with a force R through point O and a couple C. Okay, so first, let us try to determine the resultant of the given force system. So your Rx is equal to summation of forces in the x direction. Let us try to get positive for forces pointing forward. So your Rx in here is now equal to, so we have 75 pounds. Okay, so the 80 pounds and the 30 pounds has no x component because these two forces are parallel to the z-axis, and the 40 pounds in here also has no component because it is parallel to the y-axis. Let's try to determine now your r sub y. And r sub y is summation of forces in the y direction. Okay, taking to the right forces as positive. So we have again your Ry is now equal to, so we have the 40 pound force. Again, 75 has no y component because it is parallel to the x-axis. And also with the 80 and the 30 pounds, which are parallel to the z-axis. So let's try to determine now your Rz. So Rz is equal to summation of forces in the z direction, taking upward forces positive. So your Rz in here is now equal to, so 80 is going upward, so it's positive, and 30 is going downward, so we have minus 30. Hence, your Rz is now equal to 50 pounds. Let us try to determine now the resultant. So let us try to determine the resultant in Cartesian vector form. So in Cartesian vector form, the resultant is now equal to Rxi plus Ryj plus Rzk. Therefore, the resultant force is now equal to Rx 75I, and then Ry is 40 pounds, so plus 40J, and Rz is 50 pounds, so plus 50K. Now, how are we going to determine now the resultant couple moment? So if you try to get now the resultant couple moment, let us try to determine now the resultant couple moment. So this could either be C, represented by C, or N. Moment about the x-axis is now equal to moment of the resultant force. Moment about is equal to the summation of moments. So it's equal to the summation of moment of all the forces in the system about the same axis, and that is now your x-axis. At this time, let us try to consider counterclockwise moment as positive. So your mx is now equal to, that is also equal to cx, or that one is now equal to. So we're getting moment about the x-axis. Okay, the 75 pound has no moment because it is parallel to the x-axis. So we now have your 80 pounds in here. So your 80 pounds is now having, so this is the x-axis, so this having counterclockwise about the x-axis, and therefore it is positive 80, and the moment arm is 18 inches. And then the 40 pounds in here has no moment about the x-axis because it intersects the x-axis. So we have the 30 pounds in here. So your 30 pounds is now going clockwise about the x-axis. So we have minus 30, and the moment arm is equal to 18 inches. Hence, the moment about the x-axis is now equal to cx, and this is equal to 900 pound inch, or we can just write this as 900 inch pound. Now we have the moment about the y-axis is equal to summation of moment about the y-axis. Again, let us try to take counterclockwise moment as positive. So we have your moment about the y is now equal to, we call that as cy, and this is therefore equal to. So this is the y-axis. So let us try to determine now the moment. So the 80 pounds, now your 75 pounds in here, has no moment about the y-axis because it intersects the y-axis. And your 40 pounds and your 30 pounds also intersect the y-axis. Hence, the only force that will have moment about the x-axis is the 80-pound force. So this 80-pound force is going counterclockwise about the y-axis. So we now have 80, and the moment arm is equal to 9 inches. And therefore, this is equal to 720. That is now your inch pounds. Now, let's try to get now the moment of all the forces about the z-axis. Or that is now your zz, and this one is now equal to. So let's try summation of moment of all the forces about the z-axis. Again, let us try to consider counterclockwise moment as positive. So this is counterclockwise moment is positive. So your mz, which is equal to cz, is now equal to 80 and 30 pounds. We'll have no moment about the z-axis because these two forces are parallel to the z-axis. The 40 pounds has no moment about the z-axis because it intersects the z-axis. So only the 75 pounds has moment about the z-axis. And the 75 pounds is going clockwise. So we have minus 75. The moment arm is 18 inches. And therefore, your mz, which is equal to cz, is now equal to 75 by 18. So that is equal to minus 1350 inch pounds. So let us try to express now the couple moment acting at point O in Cartesian vector form. So let's try to get now your M in Cartesian vector form. So your M in here, which is equal to mxi plus myj plus mjk. So your M in here is equal to the couple, and this is equal to mx is 900. So we have 900i plus my is 720, j plus mj is negative, so we have minus 1350k. So this is the value of the couple moment which is acting at point O, 900i plus 720j and minus 1350k. Let us now proceed to distributed normal load. If the width of the loading area is negligible compared to its length, a distributed load can be represented as line load. So how are we therefore going to determine the equivalent resultant force of a straight line load? Now, the magnitude of the resultant force is equal to the area under the load diagram, and the location of the resultant force passes through the centroid of the area under the load diagram. Now, there are two types of a line load. First in here is a uniformly distributed load. Yes, a uniformly distributed load. So, a uniformly distributed load, this is distributed. So, we have the load is distributed uniformly over a span or length. Now, having an intensity W, and this intensity W, the unit of this intensity W may be Newton per meter, or it will be kilonewton per meter, or this is pound per foot, and so on. So the intensity of a uniformly distributed load is represented by small w, and the unit is force per unit length, where the length of the span where the load is distributed uniformly. So we have a uniformly distributed load. Let us try to consider that this is a span of length L. So this is now a span of length L. So the length of this span is equal to L. Now, so we have now the uniformly distributed load. So this is distributed uniformly over a certain span. So this is now your uniformly distributed load. Have. Now, so the intensity of this uniformly distributed load is now equal to W. So I'm going to consider this as point A and this one is point B. Let us try to determine now the equivalent resultant force. So this is therefore the equivalent resultant force. So I'm just going to consider this one as F. So this is the resultant force, equivalent resultant force of the uniformly distributed load, which is equal to F. And the magnitude of this resultant is equal to the area of the load diagram. So for a uniformly distributed load, you try to notice that the area is a rectangular area. Hence, the area of a rectangle is now equal to W multiply this one by L. And this is acting at the centroid under the load diagram. So where's the centroid of a rectangular area? So this is therefore the centroid of a rectangular area or a uniformly distributed load. So this is acting so the length is L, so we have L all over 2 and this one is L all over 2. Hence the equivalent force or resultant force of this uniformly distributed load is the area under the load diagram, which is WL, and this passes through the centroid of the area under the load diagram. And therefore, your F, the equivalent force, is acting at L all over 2 from point A, or that is also at L all over 2 from point B. Okay, so this is your uniformly distributed load. So we have another type of a straight line load is your uniformly varying load. So your uniformly varying load varies uniformly from an intensity 0 to an intensity W, or from an intensity W to intensity 0. So let us try to determine now the equivalent resultant force of this uniformly varying load. Now, you try to notice that a uniformly varying load has the shape of a triangle. So, what is the area of a triangle? Your F1 therefore is now equal to 1/2. Multiply this one by W, multiply this one by L. And your F2 in here is equal to the area under the load diagram is still 1/2. Multiply this one by W times L. Now, where will the equivalent resultant force act? As we have said previously, it passes through the centroid of the area under the load diagram. So the centroid of the area under the load diagram. So if we have an intensity 0 to W, then the centroid of this area So we now have the centroid of this. So the equivalent resultant force passes through the centroid. Hence, this one in here is 2/3 of L, and this one is 1/3 of L. And therefore, F1 is acting at 2/3 of L from point A and 1/3 of the length of the span from point B. So for the next uniformly varying load, F2 again passes through the centroid of the triangular area. So this is now the centroid of the triangular area. So this is 1/3 from point A. This is 1/3 of L, and this one is 2/3 of L. And therefore, your F2 is acting at 1/3 of L from point A and 2/3 or 2/3 of L from point B. Again, do not forget that the equivalent resultant force of a distributed load or distributed line load is equal to the area under the load diagram. And this equivalent resultant force passes through the centroid of that area. So we have to illustrate what a line load is. A beam is subjected to a system of loads that can be represented by the load diagram as shown. So the load diagram has an intensity of 500 pound per foot at point A, and it varies linearly to or uniformly to an intensity 250 pounds per foot 4 feet from point A, and uniformly distributed at point B. Let's try to determine the resultant of this system of distributed loads and locate its line of action with respect to the left support of the beam. So the left support of the beam is at point A. So first, let us now, you try to take note that this line load consists of a varying load or uniformly varying load and a uniformly distributed load. Let us try to divide now this loading into two, so that if I will going to extend this one in here, so this is now, okay, so we have our first load in here. So the intensity of this load is 250 throughout the span. And the intensity of the remaining load is now equal to, so this one is now equal to 500 minus, so we have 500 minus 250, so this is equal to 250 pounds per foot. Now, so let us try to consider, first let us try to consider that this uniformly distributed load is now your area 1, and for the triangular loading, it is now your area 2. Now, the equivalent resultant force of the distributed loading of this uniformly distributed load. So I'm just going to call this one in here as F sub 1. And this is now your F1. So how are we going to determine your F1? So your F1 is now equal to the area under the load diagram. And this is 250. So that is 250. Multiply this one by the length. And the length in here is equal to 7.5. And this is therefore equal to 1875 pounds. And this passes through the centroid. So it passes through the centroid. So this is at 7.5 divided by 2 is 3.75 feet from A, or 3.75 feet from point B. Now, let us try to determine now the equivalent resultant force of this triangular loading. So we have your area 2. This is now the equivalent force, and let us consider this one as F2. Again, your F2, the magnitude of F2 is equal to the area under the load diagram. So the area of this triangle is 1/2 of 250. Multiply this one by the length, which is equal to 4. And this one in here is equal to 500 pounds. And this is acting at, so this is acting at 1/3. So that is 1/3 of 4 from point A, or at so this is at 3.5 plus 2/3 of 4 from point B. Okay, so this is 3.5 plus 2/3 of 4 from point B. Okay, so that is 3.5, and this one is 2/3 of 4. So 3.5 plus 2/3 of 4 from point P. Or if I will going to consider this one in here as point C, that is at 2/3 of 4 from point 2/3 of 4 from point C. Now, so the resultant is now equal to, the resultant force is now equal to summation of forces. So you try to take note that the two equivalent resultant force of the distributed normal load are directed vertically. So I'm just going to consider that one as in the y direction. So summation of forces in the y direction. So I'm going to take upward forces is positive. So your R is now equal to F1 plus minus F1 minus F2. So your R is equal to negative F1, that is 1875 pounds, minus your F2, which is equal to 500 pounds. And this is equal to negative 2375 pounds. Therefore, the resultant of this distributed load is now equal to 2375 pounds, and this will go downward. So that is therefore the resultant of the distributed force. Now, let us now determine the location of the line of action of the resultant force. So I'm just going to consider that this is now the resultant force. Now, this is now your F1. Your F1 is 3.75 feet from point A, and your F2 is 1/3 of 4, or that is 4/3 feet from point A. Now, I'm going to consider that this is now the location of the resultant force R. So this is now your R. And your R is having a distance of x from point A. That is now your x from point A. So moment of the resultant about point A is now equal to the summation of moment of all the forces about the same moment center A. At this time, let us try to consider clockwise moment positive. So we have R. The moment arm is x. R multiply this one by x is now equal to the summation of all the forces in the system about point A. So we have F1 is going clockwise. So F1 multiply this one by 3.75. F2 is also going clockwise, plus F2 multiply this one by 4/3. So the resultant force is 2375 multiply this one by x is equal to F1, which is 1875 by 3.75 plus F2, that is 500, multiply this one by 4/3. By 4, and this is your x, therefore is now equal to 3.241 feet, that is from point A. So that is now the location of the resultant. Now, supposing our reference point is at point B. So, moment of the resultant about point B is now equal to the summation of moment of all the forces about the same point. And that is now your point B. So, this distance in here from point B is now equal to, that is 3.75 feet. and your F2 from point B. So the distance of F2 from point B, okay, so that distance from point B, so this one is equal to 3.5. So we have 3.5 feet plus 2/3 of 4. So that is plus 2/3 of 4. So the moment of the resultant about point B is now equal to the summation of moment of all the forces about the same point B. I'm going to consider now that the distance of the resultant from point B. The distance of the resultant from point B is equal to x of 1. So that I will now going to consider counterclockwise moment as positive. So your R, multiply this one by x sub 1. And this is equal to F1 counterclockwise. So F1, multiply this one by 3.75. And then plus your F2. F2, multiply this one by 3.5 plus 2/3 of 4, or 2/3 of 4 is 8/3. It's 8 all over 3. So the resultant force is 2375. X of 1 is equal to F1. 1875. Multiply this by 3.75 plus F2, that is 500. Multiply this by 3.5 plus 8 all over 3. Okay, so we have now the value of x1 is now equal to 4.259 feet from x1 is 4.259 feet. So that is from point B. So the resultant of this distributed normal loading is located 3.241 feet from point A or 4.259 feet from point B. If you add x1 plus x2, that is now the length of the beam from point A to point B.